This is a tutorial for how to calculate the concentration of hydrogen ions and the pH for a solution of a weak acid using the equilibrium expression and Ka constant. This includes a simplifying assumption that makes solving the mathematical equation easier. A weak acid is one that does not completely dissociate in water. In other words, in a water solution, the acid HA is only partially broken apart into H plus and A minus. There is some H plus and A minus, but most of the substance is still HA molecules. This means that we are dealing with an equilibrium reaction. Specifically, the equilibrium HA aqueous in equilibrium with H plus aqueous plus A minus aqueous, which is a Ka equilibrium. The equilibrium expression is Ka equals concentration of H plus times the concentration of A minus divided by the concentration of HA. To find the concentration of H plus, we need to know the value of Ka for the particular acid we are working with. We will also need to know the concentration, that is the molarity, of the acid in the solution. Let's call the concentration of HA before any acid breaks apart M. That's the initial concentration of HA. Once we have reached equilibrium, some unknown amount of HA breaks apart, call it X, leaving behind a concentration of HA equal to M minus X, the equilibrium concentration of HA. The equilibrium concentration of H plus would then be X, as would the equilibrium concentration of A minus. We know that when the equilibrium concentrations are substituted into the equilibrium expression, the result must be Ka. So we substitute. The concentration of H plus is X, and the concentration of A minus is also X, and the concentration of HA is M minus X. Solving this equation for X, which is the concentration of H plus, means we need to solve a general quadratic equation that depends on the values of Ka and M. Let's look at a specific example to see how to do the problem. So here's the problem. Find the concentration of H plus and the pH in a 0.25 molar solution of benzoic acid, HC7H5O2. Ka equals 6.3 times 10 to the minus fifth. First, let's write the equilibrium reaction for the dissociation. Benzoic acid in equilibrium with H plus C7H5O2 minus. The Ka equilibrium expression is Ka equals the concentration of H plus times the concentration of C7H5O2 minus over the concentration of HC7H5O2. The equilibrium concentrations for the three species are, for HC7H5O2, 0.25 minus X, for H plus, X, and for C7H5O2 minus X. Substituting these values into the equilibrium expression, we get Ka equals X times X over 0.25 minus X, which is equal to 6.3 times 10 to the minus fifth. We can solve this equation using the quadratic equation, which is relatively simple. However, if we can simplify this even more, the equation would be even easier to solve. We can actually do this if x is very small compared to 0.25. If it is, then when we subtract x, it does not change the value of 0.25 enough to make any difference. So we can ignore the effect of x in the denominator. The equation then becomes 6.3 times 10 to the minus fifth equals x squared over 0.25. Now, let's solve for x. First, multiply both sides by 0.25 to get 1.575 times 10 to the minus fifth equals x squared. Taking the square root, we get x equals 3.9686 times 10 to the minus third. So, rounding off to the correct number of sig figs, which is 2, we get concentration of H plus equals 4.0 times 10 to the minus third, and the pH, which equals minus log of 4.0 times 10 to the minus third, is 2.40. So here is a summary of the steps to solving a problem like this. 1. Write the equilibrium reaction and the Ka equilibrium expression. 2. Write the equilibrium concentrations, M minus X for the acid, X for H plus, and X for A minus. 3. Substitute the equilibrium concentrations into the Ka expression. 4. Ignore the x in M minus X to simplify the equation. 5. Solve for x, which is the concentration of H plus. 6. Calculate the pH from the concentration of H plus if asked to do so.